Let's take a look at number 6. We're getting into some calculations here, some heavy-duty business. All right, how many atoms are there in 2.5 moles of hydrogen? So it's hydrogen. They give us moles. They want atoms. Okay? They give. They want. So we start with what they give. 2.5 moles. This moles of hydrogen, I know this has to go away immediately, so I'm going to put it on the denominator of my conversion factor. I know I can go directly into atoms because I have Avogadro's number, which says for every 1 mole, I have 6.022 times 10 to the 23rd atoms. Now, what I'm going to do here, since there's no other form of scientific notation in this calculation, I'm just going to move that times 10 to the 23rd over here for safekeeping. And for calculations, I'll do the 2.50 times the 6.022. That'll give me 15.055. You should know by now that that is definitely not the answer that I report. 1, because it's not in proper scientific notation, and there are an inappropriate number of significant figures. Let's do the scientific notation part first. Okay, and this is too large. This decimal needs to be moved right there. Okay, the fact that I moved the decimal this way is caused by this number being too large. So when I go to change this exponent, I need to make it larger, right? Because that's why this decimal had to be moved. Next, significant figures. Okay, I have 4 significant figures from Avogadro's number, and I have 3 from the number that the problem gave us. So my answer needs to be reported in 3 significant figures. That'd be right there. That's 5. Tells me to round that up. So the number that I actually report, 1.51 times 10 to the 24th atoms. All right, B. How many atoms are there in 2.5 moles of uranium? Now you should be seeing that this is very similar to A. The only difference here, instead of hydrogen, we're talking about uranium. Okay, so we start again with what they gave us, the 2.50 moles of uranium. I know that moles of uranium need to cancel out, so I'll immediately put that down on the numerator. Denominator. Okay, down diagonal, so that it'll cancel. Oh, I didn't mark that these canceled up here. And then I'll put atoms of uranium on the top, because I know that for every 1 mole, right, 1 mole of uranium, I have Avogadro's number of atoms, 6.022 times 10 to the 23rd. Now again, just like I did in A, there's only one scientific notation part, so I'll just put that over here for safekeeping. Now, guess what? I just did that calculation, 2.50 times 6.022. So that gives me 15.055 times 10 to the 23rd. Now I'll go through the exact same steps I did up here. Okay, I'm going to move this decimal over here so it's in proper scientific notation. That's going to change the exponent times 10 to the 24th. And I can only report 3 significant figures, so I'm going to report 1.51 times 10 to the 24th atoms. And so you're sitting there going, wait a minute, but this problem is talking about hydrogen, this one's talking about uranium. How can they be the same answer? How can they be the same number of atoms? And my response is because we're not taking into consideration mass. We're not talking about mass. Yes, hydrogen, okay? Notice that I haven't pulled out the periodic table yet, okay? I haven't made my idiot reference at all. Hydrogen, very small mass. Uranium, very large mass. 238, very large mass. This question has nothing to do with mass, okay? Avogadro's number is defined as the number of particles in 1 mole. And so I can go from moles to number of particles. I don't have to take into consideration how massive each of those particles are. And so in the same amount of moles, you're going to have the same number of particles. We're not taking into consideration how massive each of those particles are or how much that entire sample weighs. That doesn't matter to this specific question. But because we haven't used molar mass yet, let's do that in C. So how many moles are present in 107 grams of sodium? Okay, so again, here's my given. Here's what I want. So I'll start with 107 grams of sodium. Now, before I even know what's going on, I know that grams of sodium need to go down here so that they can cancel. And I know I can use my molar mass to go straight to moles of sodium. And so that my unit will be moles of sodium, right? Because how many moles? This is what they want, moles of sodium. But I can't memorize stuff like this, so I'll look at my periodic table that I most certainly have out already. 22.99 is the molar mass. That means for every 1 mole, there's a mass of 22.99. Pull out my calculadora. 107 divided by 22.99. I end up with 4.6. Let's see, how many significant? I want 3 significant figures. So I'll go, okay, just do that as a 5 moles of sodium. 4.65 moles of sodium.